Ladies and gentlemen, hello and welcome back once again to the briefing room. My name is Eric Cavanaugh. I will be your moderator for today's event, which has an awesome title because it's just a very exciting area to discuss and explore. The title is Way Outside the Box, How NoSQL Solves Big Data Challenges. So folks, obviously big data is about the biggest topic that there is in the world of information management these days. Lots of things are going on. We just got back from the TDWI conference in Las Vegas where there was plenty of talk about big data. A couple quick housekeeping notes and we'll be off to the races. I will post again a bit.ly of the slides in the chat area, so feel free to go there to check it out. So there's a slide about yours truly and enough about me. As many of you know, the mission of the briefing room is to reveal the essential characteristics of enterprise software. So what we do is we cover a different topic every month. We'll get to that in a second. And we invite vendors to come into the briefing room to do a live analyst briefing. So the format involves me doing all the value proposition stuff up front for 5 minutes. Then the vendor goes for 20 minutes and gives a technical presentation to talk about what their technology is, how it works, why it was designed that way, etc. An analyst then comes in and gives a brief response and then just starts asking questions, hence the live briefing. So the idea is to reveal in conversation form what is going on here in the field of information management. So February is Performance Month. We're talking all about different technologies and how they were designed to achieve better performance, either corporate performance or simple database and application performance. Then we'll have integration in March, discovery in April, analytics in May, and June is intelligence. So let's talk about performance. And I hear some background noise in there, so just watch out for background noise, folks. So the database market has undergone this huge change. This entire world of NoSQL, which typically stands for not only SQL, has evolved in large part out of a need to improve performance for all kinds of different applications. A lot of this is web-based stuff, so a lot of big data comes from, for example, web logs or clickstream analysis or other kinds of social media, for example. There are all these kinds of devices out there, lots of monitors and sensors and so forth, creating just vast amounts of data, and it's very difficult for traditional database engines to deal with that stuff. And so we have this revolution going on in the database market. In fact, we're in the midst of a report right now, an interactive web report, looking into the database revolution itself. We have a webcast tomorrow on that. Hope you can join us for that one as well. But when we were at TDWI talking to different people, it dawned on me that a big reason why this NoSQL revolution has come to pass is because the old model simply did not allow for the kind of transactions and the kind of business and the kind of processing that is required today. Again, largely due to the web. And the interesting thing is that many of the processes that we have in the world of traditional data management, like data warehousing and ETL and data quality and data cleansing and data profiling, all of those different disciplines have become so significant largely because what we have been doing hitherto was trying to reverse engineer the world into a relational database model. Now, the relational database model has proven to be extremely resilient. It was the dominant database format for decades, but it's changing now, and I would submit to you it's going to take several years for us all to fully appreciate just how much this NoSQL revolution is changing the way business is done and the way business can be done. So our analyst today is Robin Bloor. He is Chief Analyst here at the Bloor Group. And with that, I'm going to introduce DataStax. So as some of you may know, it was set up to deliver and market a big data database based on the popular open source Cassandra, the Apache Cassandra database. In fact, Jonathan Ellis, who will be joining us in just a couple seconds, is the chair of the Apache project on Cassandra. So there's a picture of Jonathan. Now I'm going to go ahead and push the first slide here and hand the keys over to Jonathan. And my friend, the floor is now yours. And by the way, everybody, happy Mardi Gras. Jonathan, go ahead.
Thanks very much, Eric. So DataStax Enterprise and Cassandra are both part of the big data side of NoSQL. And that's not every NoSQL product is a big data product. There are graph databases, for instance, a very interesting type of non-relational database, but it's all the products out there are basically single machine databases. So for the big data scope of problems, they're not super interesting. So Cassandra and DataStax are both heavily in the big data side of NoSQL, which I think is the most interesting part of it. I think that's the most interesting challenge being solved by NoSQL databases. So when we talk about big data, I think there's a handful of things that make that up. Data can be big in the sense of data volume, in the sense I just have terabytes or petabytes of actual data to keep track of. But it can also be big in terms of velocity, in terms of how many updates per second. If I'm doing tens or hundreds of thousands of updates per second, that's another challenge in its own right. Even if you're only dealing with a small number of terabytes or hundreds of gigabytes of total data scope, if you're doing hundreds of thousands of updates per second, that's a challenge as well. And then a third challenge can be the variety of data. When you have data with thousands of different potential attributes, that can be a challenge for traditional relational databases that are only good at dealing with dozens or hundreds of columns in a row. And then finally, when you're dealing with a customer base that's worldwide, or data coming in from multiple locations, that can also be part of a big data challenge, is being able to coordinate the work that you're doing across multiple data centers. So all of these can play into whether you have a big data problem, and it tends to be the kind of thing where when you see it that you're starting to feel the pain of one of these aspects that most people starting with relational databases, that Oracle isn't able to keep pace with the velocity of updates you're processing, or the scale of the number of terabytes of data you're having to track and store. So increasingly, as people are starting to tackle these problems and wrap their heads around managing them, it's becoming clear that big data can be a competitive advantage. This is one study that was done by McKinsey showing that the companies in these different categories that are the leaders in dealing with their big data that they're generating as part of their business are outperforming their market segments. So I think that there's three main categories of dealing with big data that we can break these problems down into: scalable performance, operational ease of use, and cost effectiveness. And typically, most products out there are going to give you 2 out of 3. There's some that give you cost-effective, scalable performance, but they're difficult and fragile to manage. There's others that are scalable and easy to manage, but they're not cost-effective. Of course, Oracle is notorious for that, picking those two circles. So to get all three, I've been working for a couple years now on Apache Cassandra, and last year I co-founded DataStax to bring this to a wider audience, that Cassandra and DataStax solve all three of those circles by giving you high performance in an easy to administer, easy to manage, easy to flexibility to deal with your changing business requirements, and cost effectively. So what DataStax has done around Cassandra is build on top of it a data platform called DataStax Enterprise. And what we're doing right now with DataStax Enterprise 1.0 that we launched last year is we're marrying the real-time power of Apache Cassandra with the analytical flexibility of Hadoop. And so what that looks like is this diagram here is representing that with blue machines for the Cassandra side and green ones for the Hadoop side. And the reason why we do that, we have separate machines for each of those, is that the real-time or OLTP workload, if you will, is fundamentally different from a batch-oriented analytical workload. And if you try to do both of them on the same set of machines, the random access that the real-time side is doing conflicts with the sequential scanning that the analytics are doing and vice versa. So what we do is we pull those apart into separate groups of machines, but they're part of the same logical cluster, and Cassandra takes care of replicating between the analytical data and the real-time copy of that data to keep them in sync. So you can do things like, actually Shopify just announced software as a service that does this, where they have they'll analyze your e-commerce data and tell you that customers, they'll use Hadoop and Mahout machine learning to go through and tell you that customers who bought X also tended to buy these other products along with that, and then feed that back into your shopping cart and your catalog data that you're serving to customers in real time, and that's happening bidirectionally without having to do any manual ETL to get that data shuffling between the analytics and the real-time sides. Another part of DataStax Enterprise is DataStax Ops Center, which helps you manage and monitor your cluster for health, to know if you need to add capacity, to tell what queries are running right now and how when they'll be complete. All these things that you need to do to manage a cluster. Ops Center is there to make that accessible and easy to use. So just to briefly talk about a couple case studies. Netflix has talked extensively about how they migrated from Oracle first to Amazon SimpleDB and from there to Cassandra. So they've actually done a couple migrations in the past couple of years, and they've finally gotten to a place where they're satisfied not only with the scalability and performance that they're getting, but also with that they don't have to spend a great deal of effort managing it, and their engineers can focus on building their business and writing their applications rather than focusing on infrastructure. That's been the big win for them. So as part of that, they've migrated from actually managing their own data centers back when they were on Oracle first to, like I said, SimpleDB on Amazon Web Services, and now they're running Cassandra also on EC2 nodes in Amazon's cloud, and they've been very happy with that. They did a test as part of their migration scalability performance test against Cassandra to see, hypothetically, if we needed to do 1 million writes per second, how big a cluster would we need to get to? And they pushed it up to 288 nodes to get just over 1 million logical writes per second. And by logical writes per second, I mean that they're actually using what, as the slide says here, a replication factor of 3. That means there's 3 copies of each write or each update being placed throughout the cluster for resiliency to make sure that we don't lose data. So the cluster is actually doing over 3 million physical writes per second. And the thing I like about this is that the graph, it almost looks fake because of how straight that line is, but that is real data from real machines pushing that workload. A second company using Cassandra to solve their business problems is Uyala. They do video analytics And so this is a good story of the marriage that Cassandra and DataStax allow you to do between the real-time side and the analytical or batch-oriented reporting side. So similar to most people using Cassandra, they need the ability to scale their cluster. They need it to be elastic. They need it to be able to grow it. And they need to be able to deploy new features in response to customer demand. So datastax.com/software is where you can get DataStax Enterprise. There's a lot of resources on the site as well to let you know about, a little more under the hood, what's going on, how it solves these problems technically. And with that, I'll turn it over to Robin.
Okay. Robin, so do you want to go ahead and chime in there? I'll make you the presenter.
Okay.
There you go.
Oh, look, it works. Okay, well, just in the general sense, there was, a dream or even an expectation that a single kind of database engine would eventually cater for every type of database workload. And that dream kind of died very quickly, to be honest. It wasn't the case, but it was the case that traditional relational databases proved to be extremely versatile for a while. They were able to do transactional workloads, and they were also able to do query workloads up to really quite high volumes of data. So I guess you could say that for a period of time, the dream seemed like it might do, give it 10 years or something, might come to fruition. And that's been blown completely. The need for alternative database engines is just completely clear from the fact that a whole bunch of new database products have appeared. So first we had the column store databases, which were really a different underlying technical architecture, but really imitating in most ways what relational database did. And then we have a new breed of databases called the NoSQL databases, that really are quite different. I mean, they don't resemble column store databases in any reasonable way. And actually, there's a much greater variety. If you take various column store databases, well, they're not the same. But there's a lot that they do that's similar, whereas the NoSQL databases seem to vary in quite a dramatic way. So the first question is, well, if you're in the situation of wanting to do a database development and the products that you're currently using really aren't up to the workload that's intended, then how would you look at the products that are out there? And these are, there's nothing particularly brilliant about this. It's just these are the things you will look for. You will have some idea of the kind of performance that you want, and you will look for the kind of performance characteristics. So as Jonathan said, there's data velocity, that's an issue. There's absolute size of data, that's an issue. And there's query performance, and that itself is an issue. Then there's data characteristics. Some data is lumpy. Maybe you have a vast amount of data, but they're all kind of documents of one sort or another. Or maybe you have just log data, and it doesn't vary a whole heap, and in actual fact, maybe you've got an awful lot of sparse data, and that would be a different data characteristic. Or maybe you have, again, as Jonathan suggested, you just had a vast number of columns, and relational databases certainly don't manage that particularly well. So you would look to data characteristics, the ones that you're trying to satisfy, and the kind of products that actually do satisfy that. Then you would look for intended workload and versatility. It's an interesting idea that you might buy a database for an island system, one that you just put in a corner and you ran data into it, and it did what you wanted it to do. But it's not going to be that way. It's like, first of all, let's just throw a whole bunch of SQL queries at it, and then somebody comes along and they want pieces of that data, so you have to start pulling off subsets maybe, or maybe you want to put their workload onto it, but it's a different kind of workload. Maybe there's, really big queries rather than lots of short queries and so on. So you need to look to the intended workload you have, but also to the versatility of the particular engines you might be looking at. Finally, I would recommend that you look at the ecosystem. Databases have never come on their own. They've always come with various capabilities of data access, various capabilities of data management, various strategies that you might need to use if you're transferring large amounts of data to and from them and so forth. There's a whole ecosystem to be aware of. And that's, if you start to look at the NoSQL databases, one of the interesting things is that if you actually put, let's kind of say, metrics on that kind of thing, you won't find many that are particularly similar. Most of them are, in my opinion, have been built really for a specific target. And having been built for that target, they're broadening out their base. I mean, you would expect them to do that. But at this point in time, if you're looking for a product, then you won't be looking at 10 different products to see if any of them fit. You'll be down to a very small number. This is the big data thing. I've kind of watched this for a long time. I remember initially realizing this sometime around the year 2000, that we would gone from, tens to hundreds of megabytes to suddenly gigabytes of data. And a gigabyte database now just doesn't sound very big at all. And then by 2004, we had databases that were measured in terabytes, and by 2010, we started to see the first appearances of the petabyte databases. And what we're looking at here in terms of a database itself, rather than in terms of all the data out there, just the database itself, we're actually looking at something that's Moore's Law cubed. Moore's Law will increase CPU power by a factor of about 10 every 6 years. The databases have been increasing in size by a factor of 1,000. So the question to ask next is, will we be dealing with exabyte databases in 2016 or around there? And I would say yes, actually. I think we will. And the reason that I think we will is that it's not this revolution. If you actually look at where are the sources of big data coming from, Jonathan went through a few of them. Yes, it's in retail. Yes, it's in telco. Yes, it's in the banks. Yes, it's in the web businesses. You would expect that they have a lot of things going on, and they have a lot of things that they'd like to log. So you would expect that. But the next revolution that's going to start taking place after the mobile revolution, which is only really just off and running, is going to be the embedded chip revolution, and we're going to have sensors in everything. I don't know at which point in time, and I'm not in the business of being a complete crystal ball guy, that we'll actually start to see this emerge. But if you think about it, just putting sensors in every form of transport, sensors in every kind of pipe of any kind that exists, whether it's fiber optics, or whether it's water, or whether it's oil in pipelines, to actually be instrumenting the flow of these things. Well, that's going to be on us within the next decade, and there's no question about it. And if we actually have that glut of data, then there will be companies out there, organizations out there that do require the management of exabytes of data. And that's why, if you look at the NoSQL databases, that's why you see a fair number of them are actually focusing on performance and scale out. So just to actually clear it up, what is a NoSQL database? Well, to be honest, it's any database that calls itself a NoSQL database because either it doesn't adhere to SQL entirely, or because it goes beyond SQL and has other means of accesses, or slightly different means of access. The penalty for having no SQL interface means that all of those WYSI BI tools that you use that hope to be able to get data with SQL are not going to be able to be used on a product that doesn't have sufficient SQL capability. But apart from that, I wouldn't personally be afraid of this stuff. So, I mean, here's a number of things. Some NoSQL DBMS do not attempt to provide all of the ACID properties that we have come to expect of a database, partly because they realized they could get away with not providing some, and that would give them some leeway, because they had a specific focus. ACID properties are really necessary if you're doing transaction processing and if you want a mixed database engine that can do transaction processing and can also do fairly hefty queries. Many NoSQL databases deploy distributed scale-out architecture with data redundancy. In other words, they're not only able to do big data, but they're also able to do big data without failing. You know, we're talking about non-stop. We're talking about 100% availability. And then there's the other things that have crawled out of the woodwork, because a lot of other products that weren't calling themselves NoSQL suddenly realized that they could call themselves NoSQL. So XML DBMS using XQuery, that's a NoSQL database. Some document stores are NoSQL databases. Some object databases are NoSQL databases in that I think most of them actually provide a SQL interface, but they also provide an object interface. Some key value stores are NoSQL databases. The graph databases that Jonathan mentioned, yeah, they're NoSQL databases. And then there's the large data pools. Bigtable, which was Google's original idea, that's been copied in various ways. Yeah, those are NoSQL databases. So in other words, this slide says almost nothing except, you know, if you have more than or less than SQL support, you can call yourself a NoSQL database. So does it really matter? And I'd say, well, maybe. It depends on what you want to do with the data. But I don't think it's actually that important. So what is important? Well, you know, when I talk through these four things, and these aren't the only four things, but they're significant things, I talked to them from the point of view of looking at database products, but actually you should be looking inside the organization and saying, you know, what are the performance characteristics we require? What are the workloads that we may want to put on this data? Not now, but over the next 5 years. Because if you buy a database product and you think you're only going to use it for a year, it's because you've not been involved with databases before. Because databases, believe me, stick around. Actually, they stick around for decades. You need to be deeply interested in the data characteristics of the data you intend to collect, not just the data that you're collecting now, but also the data that you might seek to collect. You know, metadata does not remain static. Metadata is dynamic. You add tables to databases, you extend tables, and so on and so forth. You need to look at the various workload versatility characteristics of what you intend to do. And you need to look at your own ecosystem. Some people are using some of these large database products simply because they used to archive data and they realize that they can get away without archiving data anymore, and that gives them the advantage of being able to look at, you know, decades worth of data, which in some businesses might be really significant, in other businesses maybe not. And what else do we need to think about? Well, we need to think about our software data ecosystem as to how what we're going to do is going to fit in, simply because there are, you know, we don't build island systems. We may have thought we built them, but they turn out not to be islands. We need to be aware of skills, because skills will be, the skills requirement will be significantly different for different products. We need to be acutely aware of the costs. If we're going to actually deal with big data, then we're absolutely going to care about the costs of everything, not just the cost of the software, but the cost of the infrastructure, whether something functions in the cloud, that might be a really important aspect of it, and so on and so forth. And we need to actually consider the benefits. You know, we haven't, you know, jumped out of the IT world into some other world where you don't actually have to do a feasibility study and actually work out what the organization is actually going to get out of whichever database you choose to go for. So, you know, having said that, that's my background now. I have a number of questions for Jonathan that I'm sure he'll be delighted to try and field. And we'll start with data consistency. What is the data consistency model within DataStax, and what are the implications of such a model?
This is a lot of questions on one slide. Let's see how far we can get. So there's two things that people mean when they talk about consistency that actually have different answers. One is the consistency in the sense of ACID, which is, if I have, what's a good example? If I have a user and I have a one-to-many relationship with orders, can I have an order referencing a user that doesn't actually exist? So if my database takes care of allowing me to declare a foreign key that ensures that all orders actually relate to valid users, that's the consistency in the sense of ACID. The other kind of consistency is consistency in the sense of the CAP theorem. So the CAP theorem relates to distributed systems, and it says that of consistency, availability, and partition tolerance, a given system can choose two. And that's actually been proven. And so since in real-life distributed systems, you can't ignore partition tolerance, meaning network partitions, you're basically asking which of consistency and availability am I going to sacrifice. But the consistency in this sense is not the same as the consistency I just described for ACID. So the consistency in the CAP sense is when I do a read, do I see the most recent version? Am I guaranteed to see the most recent version of the data that was written? Because if you have a distributed system where you have multiple copies of the data, it's possible to design a system such that the copy that you do a read from is not necessarily the copy that got the most recent write. So you're basically choosing either I can guarantee that I'll always see the most recent version of the write, or I can guarantee that I'll always be able to read some version, but not both. I can't guarantee both at once. So in the CAP sense, Cassandra actually offers what we call tunable consistency, where you can choose on a per operation basis whether you want it to emphasize availability or emphasize consistency, because sometimes one is more important than the other. I'd say probably 60% of Cassandra deployments, the majority of queries, use what we call consistency level 1, meaning whoever gives me an answer first, let's run with that. So that does give you the potential for seeing an older version of the answer briefly. So for queries where you can't tolerate that, then we offer higher consistency levels that sacrifice the availability in exchange. And coming back to the first part, on the ACID side, Cassandra doesn't offer foreign keys because of the nature of its data model. We emphasize denormalization over doing joins. Your user data might live on different machines than your ordered data. In fact, almost certainly does. And so, trying to enforce foreign keys or doing joins at all across those is going to be performance prohibitive. So we emphasize doing denormalization instead of pursuing that version of the ACID model. Now that said, the parts of ACID that I do think are important and that we do deliver are the A, I, and D, atomicity, isolation, and durability. Unlike some NoSQL databases, we never play fast and loose with durability. When Cassandra tells you that data has that your write is complete, then it's on disk. It's in the commit log. It will be, even if the machine crashes, even if your data center loses power, it will still be there when you come back up. That's not the case for a lot of NoSQL solutions. For atomicity and isolation, when you perform a write across a given partition key in Cassandra, we do deliver atomicity, meaning all parts of that write will either happen or not happen as a group. And isolation, meaning that when I do a read, I will see that update happen as a group as well. I won't see partial updates as that update gets propagated. So effectively, Cassandra provides the A, I, and D of ACID, but not the C.
Okay. And in terms of this tunable capability, in terms of data consistency, is that something that I can tune for certain data, or is it the whole database? And the second question is, what's my leeway there? Can I say, well, I'm okay with having data that might be slightly out of date as long as it's within, let's say, 15 seconds?
So for the first part of the question, it's tuned based on queries rather than on what type of data it is. So you can treat it as a superset of being able to do it based on the type of data and just say all the queries that deal with user accounts, for instance, I'm going to use the higher consistency for. But you can actually go finer grained than that and say that when I'm running reports on my user data, I'm actually okay if I'm using slightly out of date data, but when I'm actually showing the user his own account profile, I want to make sure that that's the most recent. So we do it on a per query basis for that reason. As for do we provide time guarantees? We don't. We provide tunability in terms of how many replicas do you want to ensure are responding. So I mentioned the consistency level of 1, which is typically the lowest. There's some edge cases that I won't go into, but typically that's the lowest. Then you can go up to a majority of replicas within my data center, a majority of all replicas, or all the replicas in the cluster.
Okay, so you've mentioned replicas, and I was kind of aware that the DataStax does this multiple replicas. So if you could just, and you only need to do it briefly, if you can just explain how resilience works. Let's assume that I've got a petabyte of data out there, off an obscene, sitting over an obscene number of servers, and one of them dies. How does Cassandra perform with that?
So what Cassandra does is, first of all, in this kind of scenario, it's not going to, well, it'll do some things automatically, and other things it'll wait for you to tell it what you want it to do. And let me elaborate. So automatically, when you're querying that data that was on that machine, Cassandra will know that it's dead and route those queries to the other replicas. But what it won't do automatically is it won't re-replicate that data to somewhere else in the cluster, because what we found is that most outages are temporary, either because a switch failed, and so the nodes are temporarily offline, which to the rest of the cluster is indistinguishable from being dead, or maybe the power supply of the machine failed, but the data is still there on its hard disks, and so it will just swap out the chassis. So Cassandra will try to avoid doing massive amounts of network traffic, re-replicating that along the cluster, unless you tell it, hey, there's a what you would issue as a command called decommission, and say that this machine isn't coming back, and then Cassandra will replicate it elsewhere for you.
Okay, so that would be the exception. Normally, it will just wait for the machine to come back. And I mean, typically, how many replicas do people configure? 3?
3 is common, because what that does is that allows you to use the quorum consistency level to say, I want a majority of the replicas. I want 2 of the replicas to be part of each read and each write, so that gives me full consistency. I'm always seeing the most recent version of the writes, because the 2 that I'm doing the read from have to overlap the 2 that I did the writes to, no matter which ones I pick, and still allows one of those nodes to fail without having to tell clients, no, I can't give you the answer because of machine failures, so go away.
Okay. I think I understand that. In terms of, and I mean, this is a tough question in the sense that I'm not sure that you actually have typical implementations, and because I suspect that most of your customers are doing something slightly different to the other customers that are doing. But I'm kind of interested in, you can buy a product like this and configure it and point at a specific problem, but at the end of the day, every organization is running a software ecosystem with data flying all over the place. So I'm interested in the kind of configurations that Cassandra, not of itself, but the environment around it. Do you have integration with a lot of, do you have connections with a lot of data integration products? Are you putting Cassandra over data, but part of the activity is to pull off data marts and put them somewhere else? I mean, what's the kind of ecosystem?
That's a good question. What we're seeing is that a lot of I'd say most of Cassandra use is where companies are saying, we're outgrowing what we can do with our traditional database hammer, in one of the big data dimensions, in query velocity and data volume. We're running up against the limits of what we can manage, and it's getting more and more painful to deal with horizontal partitioning and repartitioning as our data set grows. That stuff is an operational headache once you start outgrowing single machine data sets. And so most of the Cassandra uses comes from people starting to port their software as a service or web application or in-house data collection to Cassandra. There's less of the sort of off-the-shelf solutions designed to run against Cassandra, although we're starting to see more of that, particularly in the sort of embedded database kind of area, where companies like Jive are using Cassandra as the storage for their enterprise messaging system. So what I think I can identify as a common thread here is that once companies start using Cassandra for one piece of their application, it's very well suited because of its elasticity, that you can add capacity very easily without your application ever having to know that your cluster is growing. They start putting more and more types of data in from different organizations, so that it's very much of a multi-tenant data source for them.
Right. Okay. I mean, I did, of course, do a little bit of research before doing this, so I actually have some idea, but I think the audience would probably be interested to know. You have your own query language, CQL, and now it's SQL-like. So could you kind of explain the distinctions and how difficult it is or easy it is for people to adjust to using it?
Yeah. Let me see if I can do this here. For people who want to dive in a little deeper, I have a link to a blog post I wrote a couple months ago about CQL. So I can make you the presenter if you want to share your desktop or something. No, I was just going to paste this this link in here. So I'm going to try pasting this into the chat here. Let me know if this works.
It did.
Yep. Yeah, so just briefly, the main difference is that, like I said earlier, that Cassandra doesn't do joins. So no joins, no subqueries. We're focusing on the basic select X from Y, where Z. That's the
right.
template for a CQL query.
Yeah, so if you forget joins, you've pretty much got most of, you've got select and project, basically.
Right.
Okay. I'm interested in how the schema works as well. In the general sense, because there's two reasons for asking this question. I think I actually had another one on the next slide. But it's like when you get a big data problem and you actually go at it, the normal course of events is that, first of all, you start to think in terms of designing the data structure, and you also start to have a very big interest in the database schema. So what's the situation with the schema on Cassandra?
That's a good question, too, and I posted another link to an article I wrote. The summary is that Cassandra started off in kind of the schemaless category of databases, and we've started adding the ability to do more schema in as people started, as Cassandra applications started maturing. It became more clear that the value of the schema is to allow different development teams and different organizations to use the data that they're generating within the company without having to go into the source code of an application and say, hey, what's in this table over here? Because if it's completely schemaless, I have no idea what's in the table. Only the application knows. So we've added those features back in. They're not required, so in that sense, it's kind of a schema optional database. But it's part of what I'd consider best practices now to say, this birth date column is an integer, and this email address column is a string, and that sort of thing.
Right. So well, I don't even know whether it's an easy question. This ought to be an easy question, but again, you run into a whole different areas of application. So what would you, if you were trying to describe the typical data processing situation where you thought, DataStax Enterprise was the answer, what would that be? What would you regard as the sweet spot?
That is a little bit of a tough question, simply because it is a general purpose tool, and people are using it across a wide variety of industries. That said, some use cases that come up over and over are dealing with time series data, whether it's monitoring sensor data or tracking user actions or activities on your website. That's a very, very it's a bit of a broad category, but that's something that Cassandra is very, very good at. Another one that I mentioned, Jive, using Cassandra for enterprise messaging. There's a lot of messaging companies using Cassandra. Constant Contact is another one. Advertising is another example. OpenX is basically the largest ad network outside of Google. Longtime Cassandra user. So those are some of the common areas, I would say, that people reach for Cassandra and have a lot of success with it.
Okay. And the pricing model, I mean, I'm sure everybody's got to have an interest in that. And actually, I'm kind of interested in whether it's different when you deploy DataStax in the cloud, or is it, is it just the same? It happens to be that the cloud infrastructure is probably going to be less expensive for you.
It's a per node pricing model, so we do that. That does encourage people to use the beefier cloud nodes rather than the wimpier ones. But it's very competitive, I'd say, with other offerings in the area. Like I said at the beginning of my slides, very early on in the presentation, that one of our goals is to deliver cost effectiveness as well as the performance and the operational scalability.
Well, if I was prototyping, I mean, this just came into my head, but if I was prototyping just to see if I could get stuff to happen, I'm presuming that it would be okay to just get obviously I would want a fairly large amount of data, but just to rent a few nodes on EC2, throw it in there and see how it behaves. Does that make sense to you?
Yeah, that's a great way to kind of kick the tires. And of course, DataStax Enterprise is totally free during development, so you wouldn't have to pay anything for that. And if you decide that what you really need is you just need Cassandra, you don't need the Hadoop integration or the full Ops Center management suite, then we also have a distribution called DataStax Community that's basically, it's a Apache Cassandra with a community version of Op Center that's definitely the best way to use just Cassandra if that's what you want.
Right.
And that's totally free, including in production.
Okay, I wanted to ask I was going to say who is your competition, but I'm actually more interested in who you meet in competition, because I think there's a fair amount of confusion out there as to what various products are capable of. So, do you run into the column store databases in competitive situations, or does that not happen? I'm curious as to what the territory is like out there when you're trying to sell a product of this ilk.
Yeah, we don't typically run into the column store databases because they're more in the the OLAP section. We're doing very large queries, but we're only doing a few of them kind of category. And DataStax is more interested in customers that need both. They need to do analytics, but they also need this high volume, high velocity, real-time component of running their applications. So I'd say that in terms of who we run into, in terms of people are evaluating what to move to, probably the one we see most often is Apache HBase, which is another open source product modeled on Google's Bigtable that you mentioned. I evaluated HBase as well back when I was working at Rackspace trying to decide what next generation infrastructure to work on there. And the reason I went with Cassandra rather than HBase at the time, which is still true today, is that HBase is a much more complicated architecture, and there's several single points of failure inherent in the design. And I was more interested in working on a fully distributed system because those are more they're more bulletproof because there's less moving pieces, and they're much easier to scale and make sure that that part of the system is solid. And in terms of what people are migrating to Cassandra from, by far the leader in that category is Oracle. There's a lot of Oracle users out there who are saying, well, I could pony up for Exadata, or I could look for alternative solutions, and a lot of people are looking at Cassandra there.
Yeah, right. And there's a rumor going around that Exadata can be expensive. I actually have to hand back to Eric now because we take questions from the audience at this point in time, although I have some that we can fall back on if the audience doesn't have any questions it wants to ask. Eric?
Sure thing. So let me just throw a couple questions at you, Jonathan, per the comments at the beginning of today's show. As I mentioned, we just got back from a conference last week and heard a lot of talk about NoSQL, and one of the terms that someone used was analytic offload, and that kind of got my brain thinking a bit, compounded with what you just said about Oracle. It seems to me that depending upon the use case, organizations may be able to use this kind of technology to simply unplug some of their extremely expensive database solutions. Can you walk through how someone would do that? Obviously, it's not an insignificant thing to pull off, but what would the steps look like, and how would you make sure that you're using it for the right use case and that you do it properly? Well,
that's a good question. I'm reminded of J.P. Morgan's Oracle outage that they had last year, and one analyst's comment on that was, they had this monstrous Oracle database. It took them a couple days to restore it from backup when they had some corruption. And sure, I'm sure that J.P. Morgan has some user account data that needs to be transactional and so forth. But if they're keeping massive volumes of log data and other things in that same Oracle database where it's not really a good fit, then they would have a much smaller Achilles heel when dealing with problems with that data set. So and that's kind of how I'm seeing a lot of people start that migration to Cassandra. I mentioned that the majority of these migrations are happening from Oracle, and the way people approach it is they say, well, I'm 80% of my query volume and 90% of my data volume is with these tables over here. So let's migrate those to Cassandra. That'll give us a lot more breathing room in our Oracle system while we figure out, is this working well? Do we want to migrate more to Cassandra? How hard was it for our engineers to get experience with this? And take kind of that incremental approach. I mentioned that Netflix started on Oracle, so they're a good example of this. They've blogged a lot about how they've done it, so they're a good case study in this sense. And the first part of their data that they moved to Cassandra was their bookmark data, which is when you start watching a video on Netflix Instant and you turn off your Xbox or whatever you're watching the video on, it remembers where you stopped that. So next time when you bring it up on your iPod, it picks it up on the same spot. So all that data was moved to Cassandra. And then the way they did that was they actually had their application insert. First, they did a bulk migration of the data into Cassandra, and then they started their application updating it in both the old Oracle system and in Cassandra at the same time, so that if there was any bugs in their new Cassandra code, that they'd be able to just flip a switch and go back to their kind of security blanket. And then once that was all the bugs had been flushed out, then they were able to decommission the old Oracle system.
Okay, good. That's a good answer. It really is an amazing opportunity here these days, and obviously this stuff needs to be done with assiduous care. But I went ahead and dug up the presentation you guys gave through the briefing room last year, because one of the questions here from an attendee is, what's the difference between CQL and SQL? If you can give some more details on this. And could you kind of talk about, because I know that CQL is very, very similar to SQL, and that was done intentionally, but what are some of the key differences?
So like I told Robin, the main difference is that you're not going to have joins and subqueries in CQL. We want it, it's intended for real-time, queries that need to be answered in milliseconds or less. So we're not going to be doing distributed joins. We're not going to be doing large query planning tasks, very simple queries. So this example that you've put up on the screen here, this is an example of using a full SQL query against Cassandra through the DataStax Enterprise Hive integration. So DataStax Enterprise gives you a full SQL query language with a JDBC interface and everything that allows you to do this kind of query that has the aggregation and the joins and all of that you'd expect for doing business intelligence type of work. It gives you that in the same package as well.
Gotcha. Okay, good. And let's dig into a couple other questions we have here. One of the attendees asks, do you see any chance or no chance for traditional players like Oracle, of course, IBM, to compete on volume, velocity, and even data variety criteria with Cassandra or other NoSQL databases, for example, through Exadata? And I guess one of the questions there is going to be price, because I have to think that you're providing some pricing pressure. But then we just have this whole open source movement, so I realize it may be a difficult question for you to answer, and of course you've got a bit of a bias here, but I guess how big a threat is this NoSQL movement to the traditional relational database market?
That's a good question, and there's people who make a living, gazing into that particular crystal ball. So I'll just stick to Marc-Henri's question as stated of how do the traditional players play into this at a technical level, and there's definitely always going to be room for the relational databases, and particularly in areas where you just inherently you don't really have a big data problem. There's plenty of areas out there where that's going to remain the case. And in that case, it's fine. You use Oracle, use MySQL, use Microsoft SQL Server, use MongoDB. In a lot of ways, it doesn't really matter at that level what you're going to use. Use whatever you're most comfortable with. And in that, looked at that way, most people are going to be most comfortable with, the relational databases with their many years of tooling support behind them and the infrastructure and ecosystem that comes with. So there's nothing wrong with that. Sometimes that is the best solution for the job. But in the big data space, I'm less convinced that there's that things like Exadata with their custom hardware and high price tags. I'm less convinced that that's the wave of the future.
Sure, good. Okay, and I threw up a slide here about Cassandra. This is really the one that I wanted because we have an attendee who's asking about integration with Hadoop and what analytical capabilities that can provide. Can you talk about the relationship between a DataStax Enterprise and Hadoop?
Yeah, so as this slide is trying to indicate that a traditional Hadoop stack is made up of a lot of moving pieces, some of which I've given on this slide here. And it will take someone who knows what he's doing but is relatively new to the space, to the specific software, several hours to set up a cluster of a handful of nodes with this stack, let alone be expert enough to do troubleshooting. So one of the problems, actually, I've got another link that I'll find for you on this. But one of the things that we've done with DataStax Enterprise is build the necessary parts to do Hadoop MapReduce analytics on top of Cassandra, so that you just have that single infrastructure component that you need to know and understand, and at the same time solving some single points of failure that a traditional Hadoop stack has.
Okay, good. And I'll throw just a couple more questions out here. We're going a little tiny bit long, but we always like to get into as many questions as we can. I mentioned at the beginning of the show how this NoSQL revolution really is challenging some of the fundamental presumptions upon which much of the information management industry has been based. And so it seems to me that if people start opening their minds to doing things in a new way, you can get rid of some of the problems caused by, for example, ETL. Anytime you move a large amount of data from one place to another, you open the door for some strange things to happen. And you also have this whole multiple versions of the truth issue, whereas in what you guys are talking about, you can give access to multiple sources at the same time without having to lock things down and so forth. But can you talk at just a high level about how a lot of these problems we have dealing with the relational database model, namely availability, for example, and durability and so forth, will be much smaller problems in the future if people approach data using these kinds of architectures?
Sure. And I found the links I was looking for the last question about the relationship with Hadoop. So I'll just put those into the chat as well here. So the relational systems, the reasons that they are poor fits for big data is that I think the main blame you can put most of the blame at the foot of the C in ACID that I talked about earlier, that you're committing to enforce foreign keys and referential integrity, and you're committing to allow joins computed at runtime and subqueries and so forth. And when you do these things, it's very, very difficult to deliver on scale, and it's especially difficult to deliver on increasing your scale, which is to say, I have 10 terabytes, but next year I'm going to have 20, and so I need to increase my cluster without downtime. That's very, very difficult to do. So what you saw historically is that back kind of at the dawn of time in 1999 or so, back in the Web 1.0 days, companies like eBay started running into this problem where at first their solution was, hey, we've got lots of venture capital, let's buy the biggest Sun hardware we can and run Oracle on it, and that will solve our problem. But eBay found that by 2002 they'd outgrown even the largest such system they could buy, and so they had to partition their data across multiple machines. And so this was kind of the watershed moment of big data, that saying even if we in the real-time side, which is to say that in the side of I'm having to show web pages of people's auctions from this very large data set. So eBay built that on top of, they were still using Oracle when they were partitioning their data across all of these machines. But as time went on and this problem became more common, people started asking, why am I using Oracle or a relational database at all as the container for my data when I'm not using it to provide that referential integrity, those joins at runtime? Because once I've started partitioning it across these different machines, I've given up that main feature that I wanted it for. So the Cassandra and systems like that are saying that let's, given that we can't make use of that main feature that we wanted relational databases for, what can we come up with for our new constraints of this world of big data?
Yeah, right. So here's one last excellent question to finish with. I just love the way this attendee writes the question. Isn't there a massive IT bias toward relational database management systems, not only from vendors, but also software developers in general, because that has been their whole career? Those investigating NoSQL may be considered heretics. What do you think about that?
Yeah, I've definitely seen some of that, and I think that as people start to experience this pain of this big data wave, then that's what's going to drive people to change their minds about that. If you're living in a world where your data fits on one machine and Oracle does the job, then hey, there's nothing wrong with that. There's no reason to necessarily get mad at people like me for saying that Oracle doesn't solve all problems in the world, but it certainly still solves an interesting set of problems. So I think necessity is what drives people to push outside their comfort zone, and that's the way the world's always worked, really, and there's nothing wrong with that.
Right, and I just saw a text from one of our attendees that one of the major analyst firms has predicted that 25% of current relational database systems will be unplugged by, I think, in about 5 years. So we're not the only ones who see this freight train coming down the tracks, folks. Well, folks, this does wrap up our webcast for today. You can see March begins integration. We're going to have a really interesting show next week. I'll be doing it from New York at the GARP Annual Conference. That's a risk management conference. If any of you are into risk management, go to garp.org. But big thank you to DataStax for stepping into the briefing room once again. Great job by our own Robin Bloor today, so thanks to him. And folks, with that, we will end the event, and we hope to catch up to you next time, folks. Until then, take care. Bye-bye.
Thanks, Eric.